Alright, hi there everyone. Welcome back to another episode of CS341 Algorithms. Today is going to be Lecture 8, where we talk about greedy algorithms for the second lecture. So the first thing we're going to talk about today are a class of problems called knapsack problems. So what's a knapsack problem? Well, you have a knapsack, and there are a bunch of items that you could put into the knapsack. And each of these n items has some profit. So we have a sequence of profits P, and we label the n possible profits for the n different items P1 up to Pn. These are the amounts that the items are worth intuitively. And each of these items also has a weight. So we have a sequence W of weights. And we'll label these weights W1 up to W1n. So Wi represents the weight for item I, profit Pi is the profit for item I. And then there's a capacity M that's a weight limit. So you can only hold a certain amount in the knapsack before either you can't lift the knapsack or the knapsack rips in half or something like that. So there's this capacity or weight limit M that the total weights of items you place in the knapsack cannot exceed. And all of these values are positive integers. Okay? Now, we want a solution to the knapsack problem that is feasible and optimal. So what does feasibility mean? Well, you have to respect the weight limit. So the solution is going to be an n-tuple, capital X, and we're going to label the components of this sequence, or n-tuple x. We're going to label these x1 up to xn. And intuitively, xi represents whether or not you take item I and place it into the knapsack. So an xi of 1 means you took the item and placed it in the knapsack, and xi of 0 means you didn't take it. And so to respect the weight limit, we want to make sure that the sum from I equals 1 to n, the sum over all items, of the weight of the item times this indicator variable xi, which is either 0 or 1, typically, is less than or equal to m. So if you think about it, if you don't take an item, then the weight disappears from this expression. If you do take an item and xi is 1, then wixi is just the weight of that item. So this is the sum of weights where we took the items. That should be less than or equal to m. So that's a feasible solution. It is an n-tuple that respects the weight limit. Now, there are a couple different variants of the knapsack problem that we can talk about before I mention what an optimal solution is. So there's a 0-1 knapsack problem, which is often just denoted the knapsack problem. And in the 0-1 knapsack problem, we require that each of these indicator variables xi is either 0 or 1. So you have to take the entire item or leave the entire item. The items are worth nothing if you take part of them. So think of like a new MacBook or something. If you saw it in half, it's not worth anything. So you have to take the whole thing or none of it. There's also the rational knapsack problem. It's called rational because you're allowed to take any rational fraction of the item xi between 0 and 1. So you have to think of items that are infinitely divisible. So we can just take any fraction we like of the item. It would be like if you were trying to load up on valuable spices from Bulk Barn or something. You can scoop as much or as little as you want. Xi represents what fraction of the entire quantity available that you took. Okay, and our goal in each of these variants of the knapsack problem is to find a feasible solution x that is optimal, meaning it maximizes the sum from I equals 1 to n, the sum over all items, of the profit for item I, for the total amount of item I available, times the fraction of item I that you took. So in 0-1 knapsack, the xi will be 0 or 1, so you're either going to get whole profits or no profit from an item. And the rational knapsack problem, you can basically sum up fractions of profits of different items. And at first glance, you might think that the 0-1 knapsack problem and the rational knapsack problem are really similar. And they are quite similar, at least on paper. You might think that the difficulty of solving them is similar, but you'd be wrong in thinking that, because it turns out that the 0-1 knapsack problem is NP hard, which means it probably requires exponential time to solve this problem. Now, We don't know this for sure, but we think that's probably true. Um, so this is something we'll learn more about towards the end of the course when we get into the question of intractability. But it turns out that the 0-1 knapsack problem is about as difficult a problem as we know of. It's one of the hardest problems we're aware of. On the other hand, the rational knapsack problem is solved in a fairly straightforward way in polynomial time by a greedy algorithm. So it turns out, although these two problems look really similar on the surface, they're quite different in terms of how difficult they are. Okay, so in this lecture, we're going to discuss the rational knapsack problem, and then a little bit later in the course, when we do dynamic programming, we'll talk about the 0-1 knapsack problem. I think we'll talk about that again as we get into intractability at the end of the course. Okay, so let's talk about a couple of possible strategies that a greedy algorithm could use to try to tackle the rational knapsack problem. So our first strategy is going to involve considering items in decreasing order of profit. In other words, we're going to try to maximize our local evaluation criterion PI. We're always going to try to pick the item that has the largest profit and place it into our bag if we can. Otherwise, we will place as much of it into our bag as we can. And if there's room left in our bag, if we take the whole item and there's room left in the bag afterwards, then we'll find the next highest profit item and put as much of that into our bag as we can and continue. So this seems maybe at first glance like a reasonable strategy. You're filling your bag with the most valuable items first. Well, let's try an example input to see if, to start to sanity check the question of whether this is optimal. Okay, so here's an example input. We have our profits P, our weights W, and our weight limit M. So this represents 3 items. Items that have profit 20 and weight 10, profit 50 and weight 20, and profit 100 and weight 10. And our weight limit is going to be 10. So let's think about what strategy 1 will do here. It'll make a beeline for the item with the highest profit, in this case 100, and it'll put as much of this item as it can into the knapsack. And it turns out that this entire item fits into the knapsack, so it'll just take this whole item, and nothing else will fit in the knapsack after that. So the solution is just going to be item 3, all of item 3, with a total profit of 100. And that is optimal for this example. But can you come up with an example input, where this strategy would not be a wise strategy, where you would come up with a suboptimal solution? So try to think of an input where taking the highest profit item is a bad idea. And I'll give you a moment to pause here and think about that. Okay, so I'm going to assume that if you wanted to do that, you've done that now. And it turns out that this second example input will expose the problem with this greedy strategy. So here, this is the same as the previous input, except the last item that has profit 100 now has weight 100 instead of weight 10. So if the item that has very high profit also has extremely high weight, then the amount of it that we'll actually be able to put into our bag will, excuse me, not be worth very much. So in this case, strategy 1 will lead us to take as much as we can of this last item with profit 100. We'll only be able to take about 10% of it because our weight limit is 10. And that will leave us with an absolute profit of 10, which is not very good, considering we could take half of this second item and achieve a profit of 25. So this is clearly not an optimal strategy, and this example is enough to prove that this strategy is not optimal. Okay, well, what about a second strategy where we consider items in increasing order of weight? In other words, we try to minimize the local evaluation criterion WI. So we're always picking the item that has the smallest weight. So we're going to take very light items, thinking hopefully that'll allow us to take lots of them and get a high profit. Well, is this optimal? I might give you a second to think about this and see if you can come up with a counterexample. Okay, so I'm going to assume by now that you've done that if you wanted to. Here's a counterexample. So this is similar to, in fact, this is exactly the same as our previous example. Turns out the same counterexample that shows us strategy 1 is not optimal will also show us that strategy 2 is not optimal. So we're going to pick the item that has the smallest weight, in this case the first one, and we're going to take as much of it as we can. It will actually fill our bag and we'll get a profit of 20. That's better than the profit that strategy 1 achieved. However, an optimal strategy would take half of item number 2 and would get a profit of 25. So this is a counterexample that demonstrates, that proves, in fact, that strategy 2 is not optimal. Now, there is an optimal strategy to do this. I'm going to give you a second, again, to think, to see if you can come up with what that optimal strategy would be, given what we saw about how the previous two strategies were non-optimal. Okay, so I'm going to assume that you've paused and done that if you wanted to, and it turns out the optimal greedy strategy is to consider items in decreasing order of profit divided by weight. In other words, we're trying to maximize the local evaluation criterion, profit I divided by WI. Okay, now why does this make sense intuitively? Well, ignoring weight and trying to optimize for profit doesn't make sense, because when you go for the highest profit item, I can give you an extremely heavy item. And optimizing for low weight while ignoring profit is also a bad strategy, because when you go for the lowest weight item, I can make it worth essentially nothing. However, if you try to fill your bag really efficiently to use its weight as intelligently as possible, you have a weight limit of n. Why don't you fill up that weight limit of n using the items that give you the best return per unit of weight that you consume? So if you always fill your bag with items that give you the highest profit per unit of weight that you consume, you'll use that weight in the most intelligent way to maximize your overall profit. And it should be a clue that this criterion actually involves both profit and weight and doesn't just ignore one of them. Although, of course, there would be ways that you could construct local evaluation criteria that would use both of these terms and yet be suboptimal. Okay, so let's try to see, let's look at our previous two examples and see if this strategy makes the correct decisions on those two. So here's our first example input. In this case, if we compute our profits divided by weights, we'll end up with 20 over 10 is 2, 50 over 20 is 2.5, and 100 over 10 is 10. So our highest profit per unit weight item will be number 3, giving us 10 profit per unit weight. So we'll pick that one to fill up our bag with. We'll take as much of this item as possible, and it turns out that will fill our bag and we'll end up with a profit of 100, which is optimal. Well, how about the second example input? In this case, where the most profitable item has the highest weight, it will also end up having the least profit per unit weight, so we won't choose it. Instead, as we should to get an optimal solution, we'll choose the middle item, item number 2, which has the highest profit per unit weight of 2.5. So filling up our weight limit of 10, which we can do because there is 20 weight worth of this item, more than the 10 that we need to fill our bag, we'll end up with a profit of 25, which is optimal for this input. Okay, so we're going to try in this lecture, well, we are in this lecture, going to prove that this third strategy is optimal. But before we go into proving that it's optimal, let me just give some pseudocode for it to make sure that we're all on the same page with respect to the algorithm. So here's the pseudocode. We start out with a pre-processing step, as usual in a greedy algorithm, where the first thing we do is we sort I've expressed the input here, the profits and weights, as an array of pairs. So you can think of A of I as having a profit and a weight in a pair, and I've packed them into one array just to make it easy to describe the sort. I'm going to sort A by decreasing profit divided by weight. So I'm going to sort pairs, right? And then, just for ease of reference, I could say A of I dot P and A of I dot W to refer to the profits and weights of item I, but I don't like what that does to the notation of my pseudocode, so just for the sake of notation, I'm going to split up this A into two arrays, P for profit and W for weights, after the sort. And You don't really have to think about this step as actually, being a computational step in the code that you would write. In code that you write, I would really just keep it a of I.x or a of I.p and a of I.w. But just for the sake of notation, I'm going to split this into separate arrays. So we have p of 1 up to n and w of 1 up to n, which are the profits and weights of those items after the items are sorted by decreasing profit by weight. And then we pass these arrays p and w, as well as the weight limit, to greedy rational knapsack. Now, I have some annotations for greedy rational knapsack, so I'll bring those up. So x is going to be our sequence of x1 up to xn. These are the fractions of items that we're actually choosing to place into the knapsack, and initially no items are chosen. Weight is going to be the current weight of our knapsack, and for all items, we're going to check, can the item plus our current weight, whatever the bag currently holds, plus the weight of that item, can that fit into the bag, or is that too big to fit into the bag? So if it's greater than m, it's too big to fit into the bag. So if we can't fit the whole item, then we're going to take as much of the item as we can to exactly fill the knapsack. And then once we've exactly filled the knapsack, we can just break out of the loop. So remember, x of I here is the fraction of the item that we're taking. And what's the fraction of the item that we're going to take if it can't all fit in the bag? Well, it's whatever the weight limit is minus our current weight. So this expression in parentheses is the amount of weight that's left, and it's bigger than wi. So dividing that, this is floating point division, by wi is going to give us the fraction of item I that we can fit. Okay? So, and then that's going to fill the bag entirely and will break. Now, on the other hand, if we can fit the entire item into the bag, we're just going to set x of I to 1, and we're going to add the weight of the item to our current weight. And it may happen that when we get to this line of code, wi is enough to exactly fill the bag. And in that case, we will skip over this if statement. We won't satisfy this if statement because it won't be greater than m. It'll be equal to m. The weight plus the weight of I will be equal to m. We'll go to the else case. We'll take all of that item. We'll add it to the weight. And now weight will be exactly m, but we're not breaking. Is that a bug? No, because we'll go to the next iteration of the loop. For the next, either we'll exit the loop because that's the last item, in which case it's the same as if we'd done a break here, checked if weight was equal to m, and done a break. It'll be the same as if this was the last item. If this isn't the last item, we'll go to the next iteration of the loop, and we'll check if the weight, which is now m, plus the weight of that item is greater than m, and it will be, because the weight is already m. And then when we try to compute how much of that next item we take, we'll take m minus the weight, which is exactly m. That will be 0 over w of I, so x of I will be 0. We'll take none of the next item and we'll break. So I could, after setting this weight here, test if we set it exactly to m and then break. But I like how the pseudocode is cleaner with only this single break and not having to have a redundant check, because that redundant check is really just going to get taken care of in the next iteration of the loop, if there is a next iteration of the loop. So anyway, it might look initially like there's a bug in that case in this code, but there isn't. Okay, so that's it for this code. It's not terribly complicated. And our return value, x here, note that it's either, in the greedy algorithm, going to be 1, 1, 1, 1, 1, 1, 1, some number of ones, followed by some number of zeros. So we'll either take a whole bunch of whole items and then none of the remaining items, or it'll be 1, 1, 1, 1, 1, 1, up to some xi, which is strictly between 0 and 1. Followed by a bunch of zeros, because we're going to take as much as we can of an item before moving on to the next one. So we're going to take a bunch of whole items, and then we might take a fractional item, and then we'll take none of the rest. So that just gives you we're building a little bit of intuition about what the form of this x return value is. Okay, so I want to do a quick informal feasibility argument. An argument like this should generally be good enough for assignments or the midterm or the final. So here we have an excerpt from the previous slide, and I want to prove feasibility. So what does feasibility mean for this problem? Well, it means that all of our xi's are in the interval 0 to 1, and the total weight is at most m. So one of two things is going to be true about this algorithm for a particular input. Either all of the items are going to fit in the knapsack, or and we'll break out of the loop for that reason because we just ran out of items to add, Or when we exit this loop, we'll have exited because we executed line 14, this break instruction. And if we execute this break instruction, we're exiting specifically because we added as much as we can of element I to exactly fill up the knapsack. So the weight of the knapsack is exactly m. Now, every time, if we want to understand, so this is an argument that the total weight is less than or equal to m. In fact, the weight is exactly m if we exit because of the break statement at line 14, and if we exit because we ran out of items to add, then it's less than m. Now, if we want to understand why the xi's are in the interval 0 to 1, consider that every time we write to xi, it's either a 0 because we're writing to it at the initialization of the x array, or a 1 because we're writing to it at line 16, or we're writing to it at line 13, where we're writing m minus weight all over wi. Well, what do we know about m minus weight over wi? We know that we got into this if block, so weight plus wi is greater than m. Okay, well, we can rearrange weight plus wi greater than m. Just subtract weight from both sides and then divide by wi, and we get m minus weight over wi is less than 1. And additionally, weight is less than or equal to m, we've already argued. So m minus weight is going to be greater than or equal to 0, and w of I is positive. So xi will also be greater than or equal to 0. Sorry, that's obstructed here by the box, but I'll edit the slide to show that before I post. Okay, so we've proved that xi, if it's written to at this line, has to be between 0 and 1 as well. So we've shown that xi is between 0 and 1 for an arbitrary xi, which means it's true for all of them. Okay, so that's a basic feasibility proof. I do also want to at least give you a high-level overview of what a formal feasibility argument would look like. Not that you need to make such an argument on your assignments or midterms or finals, but I thought it would be useful to see what a formal argument looks like to understand the difference between an informal argument and a formal one. Okay, so here we're going to need, at least it'll make the proof a lot easier if we make a minor modification to the algorithm. This minor modification is not going to change the behavior of the algorithm at all. I'm just going to explicitly write that the weight is equal to m after I've taken as much of an item as I can to exactly fill up the knapsack. Now, we never actually read weight again beyond this point, so this doesn't change the algorithm's behavior at all. This is just really going to be useful for one lemma in the proof where I'm going to argue about what weight is when we exit the loop. So this just makes it convenient for me to say when we break the loop, weight is m in this case. So we didn't do this in the original algorithm because what's the point of writing to the weight variable if no one ever looks at it again? Okay, so here's a formal feasibility argument. I won't go through it in great detail. I'll just give you the high-level idea, and if you're curious, just for your own curiosity, you can look at this after the lecture. So the way you prove that this is feasible formally is with a loop invariant. And the invariant is going to need to argue for all I, xi is in 0 to 1, and the weight is exactly equal to the sum from I equals 1 to n of weight I times xi, where xi is the element of our x array. And we're going to prove also that that's less than or equal to m. This is all going to be proved as part of one big loop invariant. Okay, so what are the mechanics of this? Well, in the base case, initially, weight is 0, and all of the xi's are 0, so weight will, of course, be equal to the weight of I times xi, where all the xi's are 0, because weight is 0. And 0 will be less than or equal to m, because m is a positive integer. Okay, so the base case is pretty easy. As for all the xi's being in 0 to 1, they're all 0. Okay, for the inductive step, we suppose the invariant holds at the start of iteration I in the loop, and then just so that we can actually express the values of the weight and xi at the beginning of the loop and the end of the loop iteration, let's let weight prime and xi prime denote the values of weight and xi respectively at the end of iteration I, and weight and xi are going to denote the values at the beginning of the iteration I. And the idea is we want to prove that the invariant holds at the end of iteration I. So we assume it holds at the beginning of the iteration, prove it holds at the end of the iteration. And then, of course, it'll hold at the end of the final iteration after the loop, which means the invariant always holds throughout the loop. Okay, so what's the precise statement that we want to prove that the invariant holds at the end of iteration I? It's, for all I, each xi prime is in 0 to 1, And weight prime is exactly equal to the sum from I equals 1 to n of weight I times xi prime, which is also less than or equal to m. Okay, so it looks quite a bit like the loop invariant, right? But we've got a couple primes in here which tell us these are the values at the end of the loop. Why didn't I use a prime for wi? Because it doesn't change. Okay, so this is what we want to prove. I've copied that from the previous slide, and there are going to be two cases, and I won't go through the cases. I'll just tell you what the cases are. So the first case is if we enter this if statement at line 6, and we just end up showing, in this case, as you would expect, that xi prime is in 0 to 1, and that weight prime is exactly equal to this summation, which is less than or equal to m. And we show that using a few different techniques. So very briefly, xi prime equals 1, we can show in this case, oh sorry, I said we were in the wrong case. We're actually in this else case. So in this else case, clearly we've set xi prime to 1. So that's going to satisfy the first part of this loop invariant. And then at line 12, we set weight, this left side of this expression will be weight prime. So weight prime is going to be the old weight plus wi, which is going to be less than or equal to m simply by the fact that we are in this case where weight plus wi is less than or equal to m. So this part of the argument is easy. The hard part of the argument is actually tying together the value of the variable weight prime with this summation. You have to prove that weight prime is actually semantically contains this summation. And so that's done here, and I won't go into the details for that. You can check them yourself if you're curious. The other case, which is when we get into the if statement up here, we want to prove the exact same thing, just our assumption is different in this case. So we do the same thing. I won't go through the details here. We prove that each xi prime is in 0 to 1. We prove that weight prime is less than or equal to m, and also greater than or equal to 0. We end up proving that by accident. Those are pretty easy, pretty straightforward. The difficult part, again, is tying together weight prime with the value of this summation. And so that's the stuff that happens down here. Okay, so this is just here. If you're curious, you can see it. And if you're not curious and you hate proofs, as probably a lot of you do, then don't worry about it. I'm not going to ask you to prove this formally necessarily. However, having this as a reference might make it easy if you want to write out something very precisely in an assignment to understand what kind of a very formal level of rigor would look like. Okay. So now I want to talk not about feasibility, but about optimality. And for simplicity in this optimality argument, it's not necessary to make this assumption. It's possible to show optimality even if I don't assume this, but I'm going to assume for simplicity that the profit over weight ratios of all items are distinct. So we can order all of our pi over wi expressions from largest to smallest where there's a strict inequality between each of these pairs. Now suppose that the greedy solution is x, which is the sequence x1 up to xn, and the optimal solution is y, the sequence y1 up to yn. We're going to prove actually that x must be equal to y simply because y is optimal. In other words, we're going to prove that there is a unique optimal solution that's exactly equal to the greedy solution. So what do I mean by x equal to y? Of course, it means that x1 equals y1, x2 equals y2, and so on. And then, so how are we going to do this? We're going to prove that x equals y. Suppose x doesn't equal y to obtain a contradiction. And if they're not equal, then maybe they're exactly the same for some prefix of x and y, but there's going to be some index where they differ, right? Simply because x is not equal to y, there will be some xj that's not equal to yj. Pick the smallest integer j such that xj is not equal to yj. Maybe j is just the first element, but we're going to look at the first place where x and y differ. Okay, another way of thinking about this is up to j, x and y are identical, and then at j, xj is different from yj. Okay, so here I've drawn our greedy solution x with x1 up to xj minus 1 followed by xj. On the y-axis, up and down here, we have the fraction of the item that's placed in the knapsack. This is 100% of the item in the knapsack. This is 0% at the bottom. And then on the x-axis, if you will, down here, going from left to right, we have the item number. So here's item number 1, we take all of it. Item number 2, we take all of it, and so on. And here's the optimal solution y, the solution we've assumed exists and is optimal and is different from x. And note, we chose j. J is defined as the first location where these two differ, right? So up to j minus 1, these two solutions are identical. They take the same items in the same proportions. Now, yj is not equal to xj. We certainly know that by definition of j. But can we know something more? What's the relationship between xj and yj? In particular, could yj be greater than xj? Well, it can't, because if yj were greater than xj, and the solutions x and y are the same up to xj minus 1 and yj minus 1, they each take the same amount of items 1 through j minus 1. And then the optimal solution somehow manages to pack more of item j into the knapsack than the greedy solution can. But in fact, that contradicts how the greedy solution works, because if it were possible to take these first j minus 1 items in the same proportions that y does, and then to take more of item j than it does, well, the greedy algorithm would take more of item j. So if yj is greater than xj, that tells us that it should be possible to take more of item j than x actually does, which yields a contradiction. So yj can't be greater than xj. It has to be less than or equal to xj. And in fact, because we've just said that yj and xj differ, they're the first location that differ in x and y, we have to have that yj is strictly less than xj. So basically, there's a little bit of extra room up here where we could have more of yj, because we know in the greedy solution we picked more of item j than we did in the supposedly optimal solution y. So we could actually take more of item j in the optimal solution y if we got rid of some other items to the right, because we know we were able to take everything on the left the same in the greedy solution, and yet we could get more of item j. So how much more of item j could we get? Certainly we could get xj minus yj more. Okay, now here's a question. Can y be all zeros to the right of yj? So I'll give you a second to think about that. You could pause the video and see if you can figure that out. Okay, so I'm going to assume that if you wanted to figure that out, you've done so by now. So you actually can't have all zeros after y, because if it was all zeros after y, then the entire optimal solution y would be worth less than the greedy solution x, because to the left of yj, the two solutions are identical, and yj is smaller than xj. So what that tells us is, to the right of yj, there has to be some item that's actually taken. There has to be some k greater than j, k to the right of j, such that yk is greater than 0. So there's got to be this item k, that sum of item k, yk amount greater than 0 of item k is taken in solution y. Now here's the thing. By our sort order, we're considering items 1 up to j, 1 up to n, from largest profit over weight to smallest profit over weight. So we know that item j, because it's earlier in this sort sequence, is worth more per unit weight than item k. So it actually doesn't make any sense from a profit standpoint to take any of item k until I've taken as much as I can of item j. So what if we remove some, what if we take this supposedly optimal solution and remove some of item k, and take that weight that we saved by removing some of item k, and you just fill that weight up with some more of item j. By doing so, we're taking some amount of weight from item k, and we're replacing it with the same amount of weight of item j, and j is worth more per unit weight, so that should increase the total value of the solution y. But this is an optimal solution, so you can't increase the value of it. That's going to result in a contradiction. Okay, so let's show carefully that we can actually do that, and that we will obtain a contradiction. So how much of item k should we remove? Well, since item j is worth more per unit weight, replacing even a tiny amount of item k with item j will improve the solution. So it doesn't actually matter how much weight we take away of item j and add of item k, we can just remove an arbitrary infinitesimal delta of weight, some delta greater than 0. We're going to remove that much weight of item k, and we're going to add delta weight of item j. Any tiny delta will be enough to improve the optimal solution by a tiny amount and produce the contradiction that we want. So if we want to move delta weight from item k to item j, what fraction of item k are we removing? So delta is a weight, yk is a fraction of item j. So how much should we reduce yk by? Well, delta out of the weight of k, right? We're removing delta weight, and this fraction is some weight out of the total weight. That's how you express this fraction. This is some weight out of the total weight. So the amount we want to remove, if we want to remove delta weight, is delta out of the total weight. So delta over wk is the fraction we want to remove. And similarly, the fraction of item j that we want to add is delta out of the total weight of j. So delta weight divided by the total weight of j will yield the fraction of item j we want to add. Okay, so the modified, we can take our solution y, we can copy it, and we can change it slightly to obtain a different solution y prime. Y prime is the same as y everywhere except at items j and k. So in y prime, we've taken delta weight of item k, that's a delta over wk fraction of item k, and we've taken that away and added a delta over wj fraction of item j. So you can see that reflected here. Otherwise, y prime is the same as y. Okay, so in other words, yj prime, the prime is indicating that this is modified, is equal to the original yj plus delta over wj, and yk prime is equal to the original yk minus delta over wk. We're subtracting that fraction of item k that we're removing. Okay, so I've copied the modified solution up here so you can see it. We want to show that this modified solution y prime is both feasible and has superior profit to the original supposedly optimal solution y. This, of course, will contradict the optimality of y and prove that our only assumption that we've made so far, that y exists and is different from x, is wrong, which will imply that if y exists and is optimal, it will have to be equal to x. So let's show that y prime is feasible and that the profit of y prime is greater than the profit of y. To show that y prime is feasible, we need to show that yk is still greater than or equal to 0, because yk prime, is greater than or equal to 0. So if you think about solution y, we assumed that solution y existed and was optimal. So all of y1 up to yn were between 0 and 1, and the weight of the original y was less than or equal to m. We need to make sure that we haven't changed that. Well, which parts of y have we changed to obtain y prime? We've changed yj into yj prime. We've changed yk into yk prime. We grew yj, so the danger is that now that we made yj larger to obtain a bigger yj prime, we might have exceeded 1. So we need to show yj prime is less than or equal to 1. And as we've shrunk yk to obtain yk prime, the danger is that we've shrunk it so far that we've made it negative. We've subtracted too much and made it negative. So we show that yk prime is greater than 0. And then, of course, we're going to have to show that the weight of y prime is less than or equal to m as well. Okay, so that's what we want to show. Let's show first that yk prime is greater than or equal to 0. So by definition, yk prime is equal to yk minus delta over wk. This is, of course, the fraction of item k that we're removing. So yk prime is going to be greater than or equal to 0 if and only if yk minus delta over wk is greater than or equal to 0, which is true if and only if delta, just by a bit of algebra, is less than or equal to yk times wk. Well, the original yk is between 0 and 1, because we assumed that y is a correct solution. And wk is a positive integer. So in order for delta to be less than or equal to yk and wk, and for delta to still be positive, because we want delta to be positive, we want to remove a positive amount of weight from k. Wk we know is positive. We just need yk to be positive. But we know yk is positive. So this constrains delta to be smaller than ykwk, less than or equal to ykwk, but ykwk is positive, so it constrains delta to be less than or equal to a positive number, so we can still get a positive delta and satisfy yk prime is greater than or equal to 0. So it's possible to choose positive delta so that yk prime is greater than or equal to 0. Great. So far we're doing well. Now let's show that yj prime is less than or equal to 1. So here's the definition of yj prime. It's yj plus delta over wj. So for yj prime to be less than or equal to 1, we have yj plus delta over wj less than or equal to 1. And this is true thanks to a little bit of algebra if and only if delta is less than or equal to 1 minus yj times wj. Now, we want this thing on the right side to be positive, so we aren't constraining our delta to be 0. We want to prove that this thing on the right is positive. That way we can come up with some delta that's still positive that satisfies this expression and hence satisfies this expression. Sorry, I think my cursor might not have been visible. We want a delta that's positive to satisfy this expression, while also which means it also satisfies this expression. And the fact that it's positive means we're removing a positive amount of item k, which means we're actually going to increase the profit. Okay, so we want 1 minus yj to be positive and wj to be positive. We know wj is positive. Why is 1 minus yj positive? Well, remember, yj is less than xj. We argued that a couple of slides ago, so it has to be less than 1. If it's less than 1, then 1 minus yj is positive. So this constrains delta to be smaller than some positive number, but that's fine because that means we can find a positive delta to make this statement true. Okay, so finally, let's show that the weight of y prime is less than or equal to m. Well, if you remember the optimal solution, the supposedly optimal solution y, and our modified optimal solution, remember the changes that we made to get y prime from y. All we did was we took delta weight from yk, so we took away delta weight of item k, and we added delta weight of item j. This doesn't change the total weight. So if y was an optimal solution before, it was feasible, so weight of y was less than or equal to m, and the weight of y prime is exactly equal to the weight of y. So this is proved nice and easily. Okay, so that's feasibility of y prime. Now we need to show that y prime has a better profit than y. So the profit of y prime, notice that that's just the profit of y plus our little changes, right? How our little change affects the profit. So consider the profit of y. Everything is the same in y prime except we take away some of item k and add some of item j. The fraction of item j that we add is delta over wj. So we're adding profit proportional to that fraction of item j that we added. We're adding profit pj times delta over wj. And of course we're removing some fraction of item k, so we're removing profit proportional to that fraction. So the fraction of item k we're removing is delta over wk, so the profit we're removing is pk times delta over wk. So our profit for y prime is going to be the profit of y plus delta over wj pj minus delta over wk pk. And with a little bit of algebra, we can pull the delta out front of these two expressions and combine them, and we can see that the profit of y prime is going to be the profit of y plus this thing. So if this thing is positive, then we've shown that the profit increases when we make our changes to obtain y prime from y. So we know already that we can pick a positive delta to make everything else that we need to be true to obtain feasibility true. So this is y prime. We can get a feasible y prime for a positive delta. So all we need to show is that this expression inside the parentheses is positive, which means we need to show pj over wj is greater than pk over wk. But j is before k in the sorted sequence in which we consider these items. And we consider the items with more profit per unit weight first. So we have pj over wj greater than pk over wk. So if delta is greater than 0, which we know we can set delta greater than 0 and get a feasible y prime, then delta times this expression is greater than 0, which tells us the profit of y prime is greater than the profit of y. This contradicts the optimality of y, so our assumption that x is not equal to y is bad, therefore x is optimal and is in fact the only optimal solution to this problem. So the greedy algorithm produces a unique optimal solution to this problem. Okay, so the next problem we're going to talk about is another problem that has an interesting greedy solution called coin changing. What's this? Ah, I think it's a cabinet lighting break. Oops. Nice. Are we done? Oh, there's a few more cabinets. Okay, there are a lot more cabinets. Nice. Well, back to work. Alright, so as a first example of the coin changing problem, let's consider the Canadian coin system. So we have pennies, nickels, dimes, quarters, 50-cent pieces, loonies, and toonies. Okay, well, to be fair, 50-cent pieces are old and we don't have many more, and in fact pennies are old and we don't have many more either. But let's not remove our pennies, because if we remove pennies, then we actually can't solve the problem for all sorts of target values we want to obtain, for anything that's not a multiple of 5. Okay, so let's just assume we have pennies, nickels, dimes, quarters, loonies, and toonies. So the input for the coin changing problem is a sequence of coin denominations and a target sum, t. So the coin denominations for the Canadian coin system are going to be represented as a sequence of integers, 200, 100, 25, 10, 5, and 1. Rest in peace, penny. And the target sum is also going to be a positive integer, t, in this case 155 as an example input. And the output is the minimum number of coins you need to pay the target sum, t. And also we would like to output a list of those coins. So for example, for the target sum t, we might output a loonie, 2 quarters, and a nickel. And that can be done in 4 coins, and we want to output the list, so 1 loonie, 2 quarters, 1 nickel, and also the number 4, like the maximum number of coins. Okay, so can anyone suggest an algorithm for doing this? I'll give you a moment to pause and think about it. Okay, so I'm going to assume that you've come up with an algorithm if you wanted to. I'm going to go ahead and show a greedy algorithm for doing this. So what if we sort the coin denominations from largest to smallest value, and at all steps just use the largest possible coin? So here's the pseudocode for that algorithm. So we have greedy coin changing. The arguments are d, a sequence or an array of denominations. These are positive integers in no particular order. So in this case, for the Canadian coin changing problem, we might have like 1, 5, 100, 25, 200. So they don't have to be in order. And then t is your target sum. We sort d in decreasing order. And then our used array is going to indicate how many of each coins we're going to use. And we're to return this array as our output. So if you want to see which coins were used, all you have to do is look at the index of a particular coin, considering that we're going to sort the array D from largest to smallest. So you have to understand, as the user who calls this, that, for example, used of 1 represents how many toonies, the largest denomination, were used, and so on. And if you want to know how many coins are used in total, just sum up the contents of the used array. Okay, so we're going to iterate over all the denominations, all n denominations, and we're going to specify how many of that denomination, denomination I, we end up using. We're just going to greedily take as many of them as possible. So we're going to take our current t, target sum that we're trying to hit. We're going to take integer division of that t over the value of that denomination. So for example, if t was 900 and d of I was 200, this would be 4. We're just going to use as many toonies as we can. And then we're going to subtract from t the value of all of those coins of this particular denomination that we used. So in the example I just gave of 4 toonies, we're going to subtract 800. So in the next iteration, t is going to be 100, and we would use 1 loonie. And then finally, at the end, if t is greater than 0, then for the particular denomination and target sum that were specified as input, it's actually impossible to produce that sum. So for example, if we didn't include pennies in D, then there would be all sorts of target sums t where you can't solve the problem and you just have to return fail. Otherwise, if you don't return fail, we're going to return used, which is the array of coins. Okay, so I probably should have put these notes on the screen, but anyway, they're here for your notes, and this is just the stuff that I said. So what's the runtime complexity of this algorithm? I'll give you a second to answer that for yourself. So the runtime of this complexity is really dominated by the sort. So this sort is, if it's an n log n times sort, that's going to be the dominant factor. You have to take theta n log n time to execute this sort. And then let's say it's linear time to create this used array and initialize all of its contents to 0, linear time to iterate, doing constant work per iteration, and then constant work at the end. So if you didn't have this sort, this could be done in linear time. But if you have to sort, if you don't have your coins handed to you from largest to smallest, then you have to do this sort, and you can't get away with linear time. You have to spend n log n time. The feasibility proof for this algorithm is really trivial, at least an informal one is. Either we achieve the target sum t or we return fail. So if we don't return fail, then the solution is feasible. And if we do return fail, then we wouldn't define that to be a feasible solution, and we wouldn't say we've solved the problem in that case. Okay, so let's talk about the optimality of this algorithm. Is this algorithm optimal? What do you think? So this algorithm is kind of funny because this is an algorithm that we all intuitively know because we all know how to count change. And it turns out that the algorithm is actually optimal. Let's try to build a correctness argument. So it's optimal at least for the Canadian coin system, but maybe it's not optimal for all coin systems. It seems hard to make a general argument right off the bat. So one thing you can do is you can restrict the set of inputs to an input where maybe you'll find it to a class of inputs where maybe you'll find it easier to build a correctness argument, and then maybe you'll learn something in the process of doing that, so that you'll be able to generalize those lessons to other classes of inputs. So we're going to try fixing a part of the input. In this case, we're going to fix D, the array D, to the Canadian coin system, including pennies. We're going to try to prove optimality for all target sums T. So we're only proving optimality for a class of inputs. Specifically, the class of inputs where D is fixed as the Canadian coin system and T is anything, any positive integer. So hopefully we'll be able to show optimality for this and come up with some insights that would help us prove optimality for other coin systems as well, or understand maybe that for some coin systems it wouldn't be optimal. So, okay, so let's do this. In fact, I'm just going to prove it for coin denominations 100, 25, 10, 5, and 1, and then it's an easy extension to 200 that I'll leave for you guys as an exercise for home. So we're going to make use throughout this proof of the following 4 properties of any optimal solution that are pretty easy to understand. So the first property is the number of pennies in an optimal solution is at most 4. Because if you ever have 5 or more pennies, then you can take 5 of them and replace them with a single nickel, and you will be using fewer coins. So that can't have been an optimal solution. Similarly, the number of nickels is at most 1. Because if you ever have 2 or more nickels in a quote-unquote optimal solution, you could replace 2 nickels by a dime and improve this supposedly optimal solution, which would be a contradiction. The number of quarters is at most 3 for a similar reason. You can just replace 4 quarters by a loonie. And then the hardest one to understand here is that the number of nickels plus the number of dimes is at most 2. To see why, suppose we have 3 dimes, 3 or more, then we can replace 3 dimes by a quarter and a nickel, which is only 2 coins. If we have 2 dimes, then we want to say the number of nickels plus the number of dimes is at most 2. So if we only have 2 dimes and no nickels, that's fine. But if we have 2 dimes and at least 1 nickel, we can replace 2 dimes and a nickel by a quarter. So that takes care of the 2 dimes case. What if we have 1 dime? Well, if we have 1 dime, we can have 1 nickel. That's fine. Number of dimes plus number of nickels is at most 2. And if we have 1 dime and 2 nickels, we're in trouble because those 2 nickels can be replaced by a dime. So that takes care of the 1 dime case. No dimes, well, we can only have 1 nickel. So in all 4 of those cases where you have 3 or more dimes, 2 dimes, 1 dime, or 0 dime, we were able to prove this claim in quite a straightforward way. So these 4 properties are clearly true for any optimal solution. Now the proof is going to be by induction on the target sum t, and as trivial base cases, we can take t equals 1, 2, 3, and 4. Clearly, the greedy algorithm does the optimal thing in those cases, because the only solutions are t pennies in those cases. Excuse me. Now for the inductive step, we're going to consider t greater than 4. We're going to assume that greedy makes optimal change for target values less than t, and we want to show that it makes optimal change for t. And here I'm just recalling the properties that we've argued are true of any optimal solution. So here's the proof. We're going to do it case-wise, and it turns out to be useful to do it case-wise, where each case is t greater than or equal to one coin type and less than or equal to the next larger coin type. So once we've done t greater, we're going to assume t is greater than 4, so greater than or equal to 5. Once we've assumed that t is solved for correctly by the greedy algorithm, the greedy algorithm makes optimal change for target values less than t, we want to show that for values between 5 and the next largest coin denomination, we also make the optimal change with the greedy algorithm. So suppose t is greater than or equal to 5 and less than 10. So first off, to obtain a contradiction, let's assume that there's no nickel in the optimal solution. And intuitively, if you were to make a change for t, you would include a nickel, right? So assume that there's no nickel in the optimal solution. Then, well, the optimal solution can't contain a dime or any larger denomination because t is less than 10. That means it has to be only pennies. So we can see that property 1 implies that this can't be an optimal solution because you're going to have 5, 6, 7, 8, or 9 pennies, and clearly some of those can be replaced with a nickel. So what that tells us is the optimal solution has to contain a nickel because we assumed it didn't contain a nickel and we obtained a contradiction. So the optimal solution contains at least 1 nickel, and of course greedy will choose 1 nickel for all of these t values as well, at least 1 nickel. So what that tells us is optimal and greedy match on a decision to include at least 1 nickel. So if we remove a nickel from each of those solutions, now we can consider how greedy will solve the rest of the problem for t minus 5, and we can consider how optimal will solve the rest of the problem for t minus 5. We've reduced the problem of optimally solving for t greater than or equal to 5 to the problem of optimally solving for t minus 5. And by the inductive hypothesis, we've assumed that greedy optimally solves the case where the case of t minus 5. So all we have to argue is that if we have an optimal solution for the case of t minus 5, and we have a nickel that has to be in the optimal solution, you put together the optimal solution for t minus 5 and a nickel, and you get an optimal solution for t. And that it comes really from the fact that we just argued that the optimal solution for t has to include a nickel. So we know that that nickel is part of the optimal solution. And is it possible that the optimal solution, this is the tricky part, is it possible that the optimal solution for t consists of a nickel, and then for the remaining t minus 5 target sum, it involves coins that are suboptimal? So is it possible that the optimal solution for t consists of a nickel and then a non-optimal number of coins for t minus 5? No, because if you used a non-optimal number of coins for t minus 5, you could improve the overall solution by replacing that non-optimal solution for t minus 5 with an optimal one. So we have a property here that's called optimal substructure. The optimal solution to the problem with target sum t is also it can be built out of the optimal solution to this subproblem t minus 5. So what this tells us is, that was a very long-winded way of arguing that the greedy solution for t is also optimal. And now that we've argued that in painful detail, we'll be able to argue the rest of the cases without too much difficulty, I think. So suppose now, because we've argued for t less than 10, that t is greater than or equal to 10 and less than 25. So first assume there's no dime in the optimal solution. Well, it can't contain a quarter or anything larger because they wouldn't fit in t. So that means we only have nickels and pennies in the optimal solution. And what that means is from property 2, the number of nickels is at most 1, and from property 1, the number of pennies is at most 4. So the total number of coins we can have is at most 5, and their value has to sum up to at most 9. We could have 1 nickel and 4 pennies. That's 9 cents. So we can't possibly make t. That's a contradiction. Therefore, the optimal solution has to contain at least 1 dime. Now, the greedy solution is going to take 1 dime. So the optimal and greedy both take a dime. And then now we can consider the remaining problem of solving for t minus 10, minus the value of that dime, optimally. Well, we know from our inductive hypothesis that for values smaller than t, greedy produces an optimal solution. So the greedy solution for t is also optimal, because we'll get the optimal solution for t minus 10, and greedy has a dime, and optimal must also have a dime. So we're going to end up with the greedy solution for t being optimal. Okay, so for this last case, where 25 is less than or equal to t, which is less than 100, I want to let you guys try to do this as an exercise, because doing an exercise like this might be useful if you have to make some sort of argument like this on an assignment or homework. It's nice to get a chance to try this, and then you can see on the spot if your solution was correct or not. So in a moment, I'll put up some hints or things to remember, so you don't have to go back to previous slides. If you want to try to do this from memory without having those hints on the screen, then pause now, and I'll give you a moment to do that. Okay, so I'm going to assume that you've paused if you wanted to do that. So I'm going to put up on the screen here. Here is the proof we just did for the previous case, and here are the properties. So now with these things on the screen, hopefully you should be equipped to do this as a straightforward exercise. So I'll give you a moment to pause if you want to try to do this exercise given these hints for a refresher. Okay, and I'm going to assume if you wanted to pause and do this, you've done this. So let's go ahead and see the solution. So the abstract idea here is to find one coin that has to be in both the optimal and greedy algorithm. And if it has to be in both the optimal and greedy algorithm, what we've really done is we've reduced the problem to a smaller problem where that coin is absent from both the solutions. So we're reducing it to the case where we're making change for some value less than t. So assume, because a quarter is the smallest size we can definitely use here, and we intuitively know we're going to use a quarter in the solution, and the greedy algorithm will use a quarter in the solution. Assume for contradiction that there are no quarters in the optimal solution. Then by properties 1 and 4, which are that there are at most 4 pennies and at most 2 nickels or dimes, the optimal solution uses at most 4 pennies or 2 nickels and dimes, which means the largest value that it can produce is 2 nickels and 4 pennies, which is 24 cents. So we can't possibly make change for t. So that tells us there has to be a quarter, at least one quarter in the optimal solution, and there's also a quarter in the greedy solution. And because of this optimal substructure, the optimal solution, which includes a quarter, is going to consist of the coins that is going to consist of that quarter and the coins that will optimally make change for t minus 25 cents. And greedy must contain that quarter. And so if we solve optimally for t minus 25 cents, which we know we will with greedy because of the inductive hypothesis, we can assemble the greedy solution, which is optimal for t minus 25 cents, with the quarter and obtain an optimal solution. Okay, so let's see, greedy is optimal for t. That's the proof. And just as a home exercise, you might want to try proving this for 100 less than or equal to t less than 200. So this is for a coin changing system where we have toonies now. So I'll just so you don't spoil this for yourself, I'll pause here and you can try this exercise, or I'll let you pause here and you can try this exercise, and then I'll flip past it and go to the next slide. Okay, so I'm going to assume if you want to do this, you've paused. So it's, unsurprisingly a similar approach. Yeah, okay, I don't think I forgot anything there. Oh, sorry, there is one more case. Actually, as an exercise for outside of lecture, you could also try proving this for t-values that are larger than 200. I misspoke when I said that this was the last case. So this case is introduced for the coin system where we have toonies, but in any case, I haven't shown you the final case where even for the system, the coin system that doesn't have toonies, if we only have loonies, I haven't shown you the final case where t is greater than 100, or if we include this case and cover toonies, then we need to also prove the case where t is greater than 200. So we haven't seen a case yet where we include a loonie, right? Or a case where we include a toonie. So those are left as exercises because there's nothing really fundamentally different about them, and so I don't want to bore you by going through them here. Okay, so what about other coin systems? Well, it turns out that this algorithm is optimal for the Canadian coin system. If you fill out the last couple of cases, you'll see that in all the cases, the greedy algorithm is optimal. How about for the old Canadian coin system with pennies? How about for the new Canadian coin system? What do you think? Is this optimal for the new Canadian coin system? Okay, so I'm going to assume you've answered if you wanted to, and some values can't be created at all. And indeed, we need to be able to produce both feasible and optimal solutions in order to call our algorithm correct. But if we want to talk about optimal outputs, we could talk about outputs. There's a more nuanced way of describing this. So we can talk about outputs for which an algorithm is optimal and outputs for which an algorithm is not. So even for the new Canadian coin system, this algorithm is optimal for all inputs that have target sums that are a multiple of 5. And it's not optimal, and in fact, it doesn't produce even feasible solutions for any other inputs, any other target sums. But if I asked, is this an optimal algorithm, meaning over all inputs? No, it's not. It's only optimal for a restricted class of inputs, and in fact even feasible for a restricted class of inputs. How about the old British coin system? So in this coin system we have a 1, so we can actually make every value, every target sum. So we're going to get feasible solutions, but will we get optimal solutions? So take a moment to think about that. Okay, so I'm going to assume that you've answered that if you wanted to. So it turns out that the old British coin system, you actually will not get optimal solutions necessarily if you run this algorithm for the old British coin system. For example, take the target sum 48. You could make 48 with two 24p coins. However, the greedy algorithm would pick a 30p coin, followed by a 12p coin, followed by a 6p coin. So if you're using old British coins, you actually shouldn't deal change by just going from the largest coin down to the smallest. You actually need to think ahead, do some more complicated reasoning about how to make change for the smallest number of coins if you want to optimize for that. Now, we've seen two coin systems, the Canadian coin system and the British coin system, the old Canadian coin system with pennies and the old British coin system, where, okay, we can produce all types of output feasibly because we have a unit value, but one of them is optimal and one of them is not optimal. What makes a coin system optimal or non-optimal for this algorithm? So I don't have a solid answer for you. I haven't done enough research into this problem. The research that I have done tells me this and leads me to a more challenging home exercise for you guys. So greedy turns out to be optimal. This greedy algorithm turns out to be optimal for any coin system that satisfies this property. For all coins, if you imagine ordering the coins from largest to smallest, each coin should be divisible by the next coin in that sequence. So if you have, for example, like 32, 16, 8, 4, 2, 1, that will be optimal. You will be able to optimally produce change. And it's an exercise for you to show this. I've actually included hints for this exercise, although it's still a very challenging exercise, not something we would expect you to do on an assignment or the midterm or so on. I've included these hints. They're really tiny so that I don't spoil. If you don't want the hints, you want to try it without the hints, they don't spoil the solution for you. If you want to see them, you'll have to open up the PDF and zoom way in. Now, is greedy? Okay, so this is a property such that if a coin system satisfies this property, then greedy is optimal. So in other words, this is sufficient to guarantee that greedy is optimal for a coin system. Is this necessary? for greedy to be optimal for a coin system. In other words, is greedy non-optimal for every coin system that doesn't satisfy this property? I'll give you a second to think about that. Okay, so I'm going to assume that you've answered that if you wanted to. So the answer is no, it's actually not true that this is necessary. Because if you think about the old Canadian coin system, if DJ is 25, then DJ minus 1 is 10, and 25 is not divisible by 10. And yet, the old Canadian coin system is optimal for the greedy algorithm. So this is a sufficient but not necessary condition. And I don't know what the necessary condition is. If you're curious, you might have to dig that up for yourself online. But with that, I come to the end of the mandatory content for this lecture, and I look forward to seeing you guys next time for Greedy Lecture number 3, where we'll wrap up Greedy, and we may end up starting dynamic programming, depending on time. All right, thanks for listening, guys. See ya.
Cause I'm